Okay, I guess we can start if this is okay for everyone. Hello, I'm Juliette Morris. I'm a PhD candidate in the HECA team, which is based and part of the INRIA Paris structure. And today I will present you some of my PhD work about predicting recurrent events in a survival framework. To do so, we'll be having both the introduction of a new machine learning approach for recurrent events and a concrete application in oncology. But first, I'd like to start with the motivation that we had through some clinical data. There is this specific public health situation around the world, but we focus in France with the digestive cancer. Digestive cancer is colorectal, bowel, gastric, esophageal, hepatobiliary, and pancreatic cancer. And it's one of the most frequent cancers in France with over 70,000 patients per year. And it's also the second leading cause of cancer-related deaths in France. For the time being, the primary treatment strategy is surgery, and this raises public health concerns. Typically, what are the outcomes after this first surgery for digestive cancer? What are the risks for eventual complications after this intervention? And what are eventual factors that influence the hospital readmissions eventually for some complications? So these are our drivers for this presentation, and we have access to some hospital data. The data looks like this. So we have the time since first surgery on the x-axis. It's within a 6-month period after cancer surgery. So this is why we stop at 180 days. And for each line is one patient. We can see that we have some patients that do not have any hospital readmissions after their first surgery, for example, here. And it's either during the whole follow-up, but there are also some situations where the patient stops the follow-up before the actual administrative date. Other patients, they undergo one or more readmissions and the same either over time or they stop before the end of follow-up. And we can also see that some patients unfortunately die during the follow-up, so they do not manage to get through the whole study period because they die beforehand. So the question is, how do we actually analyze these multiple events when we have many patients over time with some very different situations? Well, we have a few hints. Maybe we could focus on the presence of at least one readmission. And this is a classification problem, and we know that some solutions exist with logistic regressions, but we cannot make a difference between one or more readmissions in these cases, so it's not really adapted. A second option would be to focus on the number of readmissions so that we have the whole events. And this would be more regression problems to address this issue. But there is another problem now, is that there is no consideration of time. So if a patient undergoes 2 readmissions in 1 month, it would be maybe considered as the same for 2 readmissions over 6 months. And we can have, well, we have the intuition that it's not really the same between these 2 patients. So there is a type of analysis that gathers together both time and the presence of an event, and it is time to first hospital readmissions through survival analysis. However, we can clearly see that we stop at the first event here, and so there is no consideration of subsequent events. So the answer is that we focus on time to recurrent readmissions, and we use the survival analysis, but we make it specific for the recurrent events. Recurrent events, they are stochastic processes, and the most important thing to have here is that we get the same event, well, the same type of event over time. So we are not mixing readmissions with relapses. It should be always hospital readmissions of the same kind. And why on the classical survival analysis, we would only focus on states between no event and a first event for a patient. We now enable a patient to have a second, a third, and so on event. What is also important is the central notion of censoring, which happens when the exact time of an event for a patient may not be fully observed. Typically, if for one patient there is 2 readmissions to event within the study period and there is a third event outside the study period, then we are not able to include this third event into the data, and we say that the patient is censored. And this is also a key notion to keep in mind for the next slides. So what do we do now to, to modelize, to analyze this type of events? I am now sharing a few state-of-the-art approaches, but not all, because otherwise we'll still be here in the next morning. First, non-parametrically, there is the mean cumulative function that is in fact the expected number of events over time, and we call this quantity mu t. So it's really important also to keep in mind that this quantity evolves over time. And we have a natural estimator that is actually the mean to estimate the expected number of events. The weights here, they are based on the total number of patients at risk. This is in line with the censoring I was talking about just earlier, because a patient at risk, they can undergo an event at any time. So it's until when patients are still in the study period and they did not drop out. There are also some modeling strategies. I'm not going through all the models here, but just maybe the important facts to keep in mind is that we have conditional models on one hand, with the Anderson-Gill model that is the most used model for modeling recurrent events with a survival framework. And this model, they focus on intensity, which is the instantaneous probability of observing any event in a small time period, as opposed to marginal models, where the interest is more in marginal features, like marginal mean or marginal rate. The main differences between these two domain models is that one necessitates full specification of the recurrent event process for conditional models, while the other doesn't require any specific dependence structure. I was talking about censoring. We all, statisticians, really enjoy when everything is independent, but sometimes in real life, this doesn't quite happen. There was an example with this patient who died, and literally death prevented from subsequent event. So we can no longer ignore that this type of censoring is non-informative and hence independent. So there will be some strategies to adjust to take into account death, and we call this event a terminal event. So with a terminal event, we take into account the survival function of all patients through the non-parametric estimator that was introduced by Gosh and Lin in 2000. And this estimator is from Kaplan-Meier, so we have a weight on whether or not the patients over time are still alive. With this specification, we make really the difference between alive and at risk, rather than censored and dead. On the modeling side, so we are also enabling, it's an extension of this non-parametric estimator, also introduced by Gosh and Lin, and we have both possibilities of having either said, so all the characteristics of the patient as time independent or time dependent. So now we have a little bit of all the context in mind. As statisticians, we have a few questions. Typically, how do we do when we have high dimensional data? So it can be either a large number of observations, either a large number of covariates. How do we select independent variables? Because, well, per constructions, we have regression models that require independent variables. So how do we ensure these situations when we deal with recurrent events? And finally, typically we would like to maybe have some generalization of our predictions on a more larger population, and we want to avoid overfitting because we do not want the model to be too specific about the data that it was trained on. Currently, well, I guess we all know that machine learning has its entrances in all addressing these challenges, and there are many survival counterparts that exist and that are actually used, but it's limited to the classical survival framework in the sense that it's only the time to the first event scope. However, we made a detailed state-of-the-art and literature review, and there is no ML algorithm to date that would be specifically designed for recurrent events in a survival framework. So this is typically what I will introduce now, is this first machine learning algorithm for recurrent events, combining both statistical inference for recurrent events that we had a few hints on, and ensemble machine learning. Ensemble machine learning is some methods that actually grow on weak learners, and for instance, growing trees. To grow trees, we have a few key components that we enable a root node to divide in a few branches, and each branch is a decision that we are able to make. And recursively, we make the decisions at each node until a terminal node. So to do the decision, we call a splitting rule that we can adjust. And the terminal node estimator requires a suitable estimator for the quantity of interest, for example, the survival function or the cumulative function of hazard. And also the last component is when do we stop the tree to grow, and we can apply many techniques to do so. So now from the growing trees, we go to growing survival trees. So we are not yet on the recurrent event scope, but Ishwarwan introduced the survival trees, where the splitting rule is the log rank test, which is an extension of the key2 test specific for comparing two survival functions. So for example, in our data, we have patients with a Duke's index that would then go either A, B, C on the left or D on the right, and so on until a terminal node that is estimated through the associated estimator, which is the Kaplan-Meier for survival functions. Here, the pruning strategy that we forced is that we wanted to have at least 15 subjects in each terminal node. So we have nodes that are quite high with 174 individuals, while others with 19 or 22 individuals, and the associated plot for the Kaplan-Meier estimator of the survival function. I will just pause because I can see in the chat. Okay, never mind. So going back, we have seen the growing survival trees part, and now we go with the recurrent events, which is the major contribution of this talk. And there are two cases, one without terminal events, so we do not consider death to be informative, and one with a terminal event. And here we have our bucket list of the key components that we should be filling in when we grow some survival trees. So the splitting rule, so remember it was the log rank test statistic for a survival tree. And now we use either a pseudo score test, that is an extension of the log rank specifically designed for recurrent events, and is associated with the MCF estimator that we have seen a few slides ago. On the other hand, we have the situation with a terminal event, and we include a modelization step through a Gaussian model that we also just saw, and we will retrieve the valid test of the associated variable that we are looking at for this specific node. And then we estimate the MCF, same by taking into account the survival function as a weight in the MCF estimator. For this pruning strategy, we are staying classic, and we would require a minimal number of events and or individuals in each terminal node. Now, so we know how to grow trees with recurrent events, and if we grow multiple trees, then we get big B trees and our MCF estimators over time. And we aggregate this to have a random forest ensemble estimator. We also can do this because each tree is grown on an independent bootstrap sample. And this goes with, so the in-bag samples where the individual is actually selected within the tree, and the out-of-bag sample where the individual is not selected at this bootstrap sample. And this is very convenient because by construction, random survival forests do not require any specific external validation data where we would like to have the performance done. And this is to say, so we will go through three performance evaluation metrics, starting with the concordance index, the C index, which is widely used in survival analysis. And so this C index is based, is the proportion of concordant pairs over time. And there was an extension proposed by Kim a few years back. But these extensions did not take time into account, while it's a bit of a shame with recurrent events because time is a key component of our analysis. For this reason, we introduced the occurrence rate. So we want the occurrence rates between observed and predicted for two different patients to be concordant at the end of follow-up. A second metric is the MSE. It was developed last year, also by a French guy named Olivier Boisis. And the idea is that we have, well, the mean square error between real and predicted number of events over time. So we implemented it for each tree B. I said real, so we would expect more like a mu value here, but we do not have access to the real mu value. Also, because the data is censored, we do not get to have all the information, all the events for all patients. So for this reason, we need to include a weight, that is the conditional cumulative distribution function of the censoring. In presence of a terminal event, this reduces also to the survival function. So this was just for one tree, and now we get an overall estimator for the ensemble random forest, that is the big MSE. But two different models may lead to similar MSE values over time. So there was a need for a score to represent the prediction gain compared to a reference estimator. Typically, it would be either the null model or the non-parametric estimator. And we defined for each tree the score as the difference between the MSE from the reference estimator and the MSE from our current estimator of our tree. And same, we aggregate to have an ensemble metric over all the B trees. We also have the importance of variables that is widely used in random forest, should they be either survival or, in this case, for recurrent events. The idea is that we first estimate the original model error, named error OOB, because it's on the out-of-bag sample, from a chosen evaluation metric. So, for example, MSE, because it's already an error per definition. And for each feature, we get to permute this feature in order to break the association between the feature and the target vector. We estimate the new error generated within this permuted feature matrix, and we calculate the difference between the error of the perturbed feature matrix and the original model. For this reason, if a variable is very important, we are expecting that the error will be very, very high after permutation. On the other side, if the error is quite null, then we would expect the error of the permutated feature matrix to be more or less the same than the original one. Back to the data I was talking about at the beginning of the talk, we applied this to the French digestive cancer data. We have some great performances overall because the C-index, we want it to be closer to 1. It's between 0 and 1, 0.5 being equivalent to random model. So here, 72% is quite adapted. The IMSE is, well, we want it to be the lowest as possible, while the I-score, we want it to be the highest as possible. Through the importance of variables, well, this is a bit, I don't know if you can all read, but we really identified 3 groups of variables from the most important ones to the least important ones. And while we do not have access to any p-values by construction, we can at least have a rank of variables that are actually important and that have an impact on our number of recurrent events over time. So to wrap up, I just presented a kind of motivational clinical data, but it is to keep in mind that there are many applications in the medical field that are really adapted to apply our model that is named RecForest. It can be in oncology as soon as we have multiple events like relapses or progression. In chronic diseases, as soon as we have multiple episodes over time, it can be applied. Any type of surgery, really, because we can get many complications after the initial surgery, like in our case. And also in cardiovascular events, which is in fact very handy for recurrent events, typically with heart failures over time. So key takeaways for RecForest, which is our model that we introduced to analyze recurrent event data with the survival framework, is non-parametric. It is also robust to multicollinearity. It is also capable of handling high-dimensional data, and we provide a few insights of data within the variable importance. We also saw 3 metrics to evaluate the performance of our model. This is not only restricted to random survival forest, but it can be applied to any recurrent event in a survival framework model. So in the end, this is a powerful and flexible tool, and it may be applied in many medical fields, as we have seen. And it is also possible that there are many extensions based on these trees, because we know that machine learning, as long as we have a weak learner that is quite efficient, there are many extensions that exist, such as boosting techniques that are actually tree-based. These are my references, and thank you for your attention. I'd be happy to answer any questions. Okay, well, if there is no question, I'd like to really thank the whole organization team. And I'm very happy to be part of this International Day that really spotlights on women in data science and statistics. Many thanks. Bye.